Okay, so I think we're ready to start the first tutorial for today. So Eli Heyes is going to walk us through string theory compactifications and Mapping manifolds and the flat metrics.
I'll just turn this on.
Must be green.
Yeah. Okay. Cool. So this tutorial is not going to be computational. We're going to just do some pen and paper problems. But if you do finish early, then raise your hand and I can give you some extra computational problems to get started with. So yeah, they've just written a quick outline of what we're going to do. You heard Lara speak this morning, so it should be fresh in your mind what she said. But I'm going to give a quick recap on manifolds, and then yeah, the two problems are up on the board. The first one is very simple. I think most of you have probably done some sort of geometry in your undergrad, so should whiz through question one nicely. It's just, first of all, proving that S2 is a real manifold, and then proving that S2 is also a complex manifold. Then I'll just do a quick recap on some Kähler geometry and complex projective space. We've had both Lara and Al talk about complex projective space, so there'll be a little bit of repetition there, but I don't think that's necessarily a bad thing. And then, yeah, we'll move on to question two. This one is a little bit more involved and will take a bit more time, but I'm going to give you a few hints, so hopefully it won't be too difficult. So I'm just going to very briefly repeat the definition of a manifold, both a real and complex. So starting with a real manifold, this is defined using an atlas. We have a set of charts, U alpha and phi alpha, where the U alpha are open subsets in M. So, manifold is M, and then these phi alpha are maps from U alpha to Rn, and we have to have two conditions for it to be a manifold. First of all, M must be covered by our open subsets U alpha. We take the union and we have to have M. And our second condition is that if we have a non-empty intersection of two of our open subsets, then the composition map U alpha, U beta minus 1 must be a diffeomorphism, as Lara said this morning. So when we're proving that something's a manifold, basically we just want to find an appropriate atlas and prove that these two conditions hold. So that is a real manifold. And then similarly, we have a complex manifold. Is again given by an atlas. It's U alpha. This time I'm going to call it Z alpha. This time, instead of mapping into Rn, our Z alpha are going to map from U alpha to Cn, because we're dealing with a complex manifold, and our transition functions. So again, if there's a non-empty subset, we take this composition map, and this has to be holomorphic in terms of the holomorphic coordinates rather than the anti-holomorphic. So these are our two definitions, and this is all we're going to need to tackle problem one. So I think I'll give you 15 minutes or so to have a go at the first part of problem one. Raise your hand if you have any questions, and then I think I'll go through part one on the board so that we're all together. Yeah, give me a wave if you need help. Okay, I think that's probably enough time for you guys to have a go at it yourself. And no one seems to want my help, so I guess that means you're finding it super easy. But in case you're sat there struggling in silence, I'm going to go over the first part anyway, and it also gives me something to do. So we can define S2 in terms of its embedding in R3 as a set of points that satisfy this: x1 squared plus x2 squared plus x3 squared is equal to 1. And so we need to find an appropriate atlas. So the first chart that I'm going to consider is basically the whole sphere except from the North Pole. This is our U1. And then we need to find our phi1. And to do that, I'm going to do this stereographic projection. I'm going to take the line from the North Pole all the way down to this 2D plane, x3 is equal to -1. And so it's going to hit a point on S2. And that point on S2 that it intersects with this line is then going to correspond to this point on the x3 equals -1 plane. I'm going to give that coordinates y1, y2. And so y1 of our point on S3 is going to equal y1, y2. So we want to find expressions for y1 and y2 in terms of x1, x2, and x3. And so to do that, I'm going to come up with a parameterization of this line from the North Pole down to this x3 equals -1 plane. So we can write this so. And now we want to find the intersection with the plane when x3 equals -1. So we have -1, just considering the x3 coordinate, 1 plus t times x3 -1. Rearranging, we can find out what t is. We have 2 over 1 minus x3. So our x1 and x2 coordinates on this plane are just t x1, t x2. So we have y1 is equal to 2x1 over 1 minus x3, and so 2x2, 1 minus x3. So this is our first chart in our atlas, and we need to find a second chart. Basically, we're going to do the exact same thing, but instead of removing the North Pole, we can remove the South Pole this time. So this time, removing South Pole, and we're going to consider the plane x3 is equal to +1. And again, we take a line from the South Pole this time to this plane. It's going to intersect the S3 at a point, and then it's going to be mapped to a point in the plane. This time, let's give it coordinates Z1 and Z2. And you can do the same procedure that I did with our first chart, and you're going to have your second map. And I'll let you guys do this explicitly, and I'll just give it to you. This time 2x1 over 1 plus x3. And similarly, 2x2, 1 plus x3. So we have our atlas. We just need to check the two conditions I wrote down earlier, that the manifold is covered by the two open subsets, and we have a diffeomorphism in our transition function. So, I mean, the first condition is obviously satisfied. If you take the the union of U1 and U2, you have S3, so that's fine. We just now need to have a look at our transition function. It's going to be this. we already have an expression for phi2. We just need to find the inverse of phi1 and then find out this composite map. So to find out the inverse of phi1, this time we need to write x1, x2, x3 in terms of y1 and y2. So to start off with, I'm going to write y1 squared plus y2 squared is equal to, just using the expressions I gave earlier, 4x1 squared plus 4x2 squared over 1 minus x3 all squared. And now I can use the definition of S3, which I said was x1 squared plus x2 squared plus x3 squared is equal to 1, to remove x1 and x2 and just write this in terms of x3. Now I have 1 minus x3 squared on top, and a 1 x3 squared on the bottom. And now we can simplify this further. This becomes 1 plus x3 on top and 1 minus x3 on the bottom. And then we just need to rearrange this to get x3 in terms of y1 and y2. And I'm going to sort my notes for this so I don't get it wrong. We have y1 all squared plus y2 all squared minus 4 all over y1 squared plus y2 squared plus 4. So we've done step 1, we found x3 in terms of y's. Now we just need to do the same for x1 and x2. And to do that, I'm just going to use what we had as our original definition of y1 and y2, and then substitute in our expression we've just found for x3. And we get, I'm leaving out all of the boring rearranging steps for you guys to fill in. Just writing the answer. And same for x2. So we have our expressions for x1, x2, x3. We can put it together into an expression for phi1 inverse. This is going to act on coordinates in our plane, y1 and y2. And rather than just writing out using it, I'm going to label this 3, this 1, and this 2. And then we just substitute in these expressions. And then the final step we need to do is just need to compose this with phi2. And again, I'll leave you to fill in the details of this, but you basically just do this phi1 inverse first and then act on it with phi2, and you get is our first coordinate, and we can see this is a diffeomorphism. So we've proved that manifold is covered by the open subsets, and our only transition function, we only have 2 charts, is a diffeomorphism. So we have that S3 is a real manifold. Any questions on that? If not, then have a go at the second part of problem 1. It's again very similar to what we just did, but this time you're having complex coordinates and you have to show that your transition function is holomorphic. So yeah, maybe I'll give you, it's quite a quick one to go through that part, so maybe 5 minutes, and then I will run through some recap on the Kähler geometry, and then you guys can try problem 2. And yeah, again, raise your hand if you need my help with anything. Okay, I think I'm gonna move on now and do a quick recap on some of the Kähler geometry and the complex projective space, things that Lara talked about this morning. And this will help you to solve problem 2. So on a Hermitian manifold, we have sometimes called the fundamental form, sometimes called the Hermitian form, which is given as I, J, I, J bar, D, Z, I, wedge, D, Z bar, J. And then a Kähler manifold is such that you have Kähler form, so your fundamental form vanishes when you take the derivative. Then your J is called a Kähler form, and just to note that often when you're talking about Kähler forms, this J is notated as omega rather than J. And Lara showed us this morning that for Kähler manifolds, you have this structure that if you take the nth power of your Kähler form, this actually gives you a volume form. And for a Kähler manifold, you can write the Ricci 2 form as minus I del bar log determinant of G. So this is going to be important when we come to solve problem 2 in a second. So that's a little summary on some of the Kähler geometry, and then the stuff on our complex projective space. As I said, Al also talked about this as well, so you should be pretty familiar about this by now. But just to remind you, it's a set of lines, set of complex lines that go through the origin. So these 2 lines will correspond to the same point in projective space. And so you can write that as lambda is some non-zero complex number. And you can define a set of charts on your complex projective space just by setting one of your coordinates equal to some non-zero number. And then you can define some local coordinates on these charts. By dividing the remaining coordinates by the one you set to some non-zero number. And then the final thing I want to mention is just to remind you, we have the Fabini studiometric on complex projective space, and the form is given as Gij bar is equal to del I del j bar log of sum of the squares of the coordinates. So yeah, problem 2, it says we want to show that if we have a d degree hypersurface in our complex projective space, then the Ricci form on this hypersurface is given by n minus d plus 1 times the Fabini studiometric plus some extra total derivatives. And this means that if in the Ricci flat case, we have a metric in the same class. So I'm going to give you just a few hints on how you go about solving this problem. I don't want to give you all the answers, but just a hint on where to go. So obviously, we're working in complex projective space, so you're going to be needing the Fabini-Studi metric, and it's sufficient to work in a patch. As I said, you can set your patches, basically just set one of your coordinates equal to some non-zero number. So an easy one to work with is just U0 where Z0 is set to 1. I would advise working in this patch, and it's sufficient to do the whole computation on this patch, but also where the nth partial derivative of your polynomial that defines your hypersurface is non-zero, as well as being on your hypersurface. This is and then yeah, f is some degree d polynomial. And a few extra hints for you. It's going to be important to use the hypersurface condition that df is equal to 0. Remember, this is the sum of the partial derivatives. And another little hint is, so we're dealing with the Fabini-Studi metric, which I've written up there, but we're working in the patch U0, and I'm just going to give you the expression for the Fabini-Studi metric on the patch. If you do finish early, actually, this might be a nice exercise to prove this, but for now, I'm just going to give it to you. It is and then you can also actually, the inverse might be useful as well. And that's just and then, so yeah, basically this whole idea of this problem is to compute the nth power of your Taylor form on your complex projective space, and then you restrict it onto your hypersurface. So basically, the whole idea is find some expression, the nth power of your Fabini-Studi Taylor form, where the nth power just means the wedge product n times. So you're going to want to find some expression for the nth power of your Fabini-Studi Taylor form, and then you're going to want to parameterize it in terms of this. I'm just going to give you this as a hint, because otherwise it's quite hard to see this. And then once you have your expression for omega to the power of n, you're then going to want to substitute it into this expression here. Any questions? I'll be around. This one's it's not so obvious to see when you first do it. I will be putting the solutions up. I'll give them on to Andre and hopefully put them on the website. So if I don't get around to you and you want to figure this out later on your own, then we'll have them on the website for you. Any questions immediately now? So I've just been made aware of my confusion in reading D as derivative rather than D as degree. So this, in case you're trying to use this, 0 equals D where D is the degree times F. Yeah, degree of your polynomial F. Yeah, this is just me reading things wrong and seeing D as derivative. And then you also have, obviously, standard. I was just mixing these two up. So yeah, if you were using my mix of these two earlier, I'm sorry, these are the two correct ones now. But this is the derivative, obviously. Sorry? This one, it says in the notes that it's f vanishes on x, and since f is a homogeneous function of degree d, that's where this comes from. Yeah, this is because f is 0, x, and f is homogeneous. No, I think this holds on x. Why have this? Yeah, that's a good point. I think this is just because kind of sort of forget this. They're just using this side is equal to 0. It just helps you. So this, yeah, obviously f is 0, which is why you get this. But this like helps you. This is equal to 0 because then you can rearrange and get this in terms of this. So it's really this equation, this part on the right-hand side equaling 0. It's not a homogeneous equation. Apparently it comes because f is homogeneous. Yeah. You're going from 1 to n, so yeah, it's on u0. So these are your patch coordinates. Yeah, I haven't actually gone through the reasoning for this. I can do that quickly now. I might just make one more comment. I made a bit of confusion with my G's. So okay, I think we've run out of time, but yeah, sorry for this confusion. I have found a proof now of this. So yeah, if f is a homogeneous polynomial of degree d, then you can write this expression here. And if you, I'm going to add this into the solution that I'm going to put up on the website. And if you want to go through it with me at a great time, come find me. Otherwise, yeah, thanks very much.